This is a GET question from analog filters and it appeared in the electrical engineering paper. But similar types of questions have also appeared in instrumentation engineering as well as in ECE GET questions. So here is the question. Consider the circuit shown below. The magnitude and phase of the voltage transfer function are respectively option A 1 and 2 tan inverse omega RC, option B 1 and negative 2 tan inverse omega RC, option C 2 and then the phase is tan inverse of omega RC, and option D is half and phase is tan inverse of omega RC. And this is the corresponding circuit that has been given. So this is an active filter, as is understandable because there is the presence of an operational amplifier here. And these sort of questions can come in various forms. So one of the pattern is that whatever they have asked in this question, so they are asking for the magnitude and phase response. The second pattern could be that you have to identify what type of filter this is. So whether it's a high pass filter or low pass filter and so on. Sometimes they might even ask for the voltage transfer function itself rather than asking for the magnitude and phase. So let's look at how we can go about solving this problem. So with any op-amp based circuit and you have presence of negative feedback, we have to target for finding out the voltage at either this node, that is the terminal which is connected to the inverting input, or this node which is the connection to the non-inverting input terminal, and then we can use the concept of virtual short and claim that the voltage at this node and the voltage at the other node, so the inverting and non-inverting input terminal voltages are the same. Now looking at this part of the circuit, so this is a voltage divider network in a sense that you have, instead of having a resistor here, it is replaced by a capacitive element. And the best way to go for solving these sort of questions is to go to the Laplace domain. So you can easily substitute C by 1 by SC, which is the capacitive reactance in the Laplacian domain, and then the time domain function Vi becomes Vi of S, and the output function V naught T will become V naught S. So with this divider network, we can frame the expression for the voltage at this node. Let's call it V of S, and this will be equal to this impedance. So this is 1 by SC divided by summation of R plus 1 by SC multiplied by VIS. And so this V of S, the voltage at this node, is given by 1 by 1 plus SRC multiplied by the input voltage VIS. Note that this is very similar approach to what we have done previously. So if we had two resistances, let's say R1 and R2, forming a voltage divider like so, we would have framed this expression as this resistance divided by summation of these two resistances multiplied by the input voltage. So instead of a resistance, it has been replaced by a capacitive element, but the approach remains the same. So what we have managed to find out is the voltage at this node, and from the principle of virtual short for an ideal op-amp, we can note that voltage at the other node, this node, will also be the same as V of S. And therefore, we can now only concentrate on the top part of the network. And we can frame the expression as, if I call this current as I1 and this current as I2, then I1 should be equal to I2, because we know that with an ideal op amp, no current can enter the input terminal of the op amp. So if I1 is equal to I2, then for I1 we can apply Ohm's law and we can frame the expression for I1. So I1 will be equal to VIS negative of Vs divided by R, and then similarly I2 can be formulated as V of S negative of V naught S divided by R. And so from this expression, we can frame V naught S as 2 times V of S minus of VIS. And then we have already found out the value of Vs. So if we substitute this value of Vs as 1 by SRC multiplied by VIS in this equation over here, then V naught S by VIS, which by definition is our voltage transfer function, will be equal to 1 minus SRC by 1 plus SRC. So for one pattern of questions, this will be our answer if they are only asking for the voltage transfer function. So voltage transfer function is the ratio of output voltage to input voltage. Now going ahead, we are looking for magnitude and phase, and therefore we have to convert the Laplacian domain expression into a Fourier form. So you can substitute S with j omega to the previous equation, and this becomes 1 minus j omega RC divided by 1 plus j omega RC. Now for magnitude, we follow the rules of a complex variable on how to find out the magnitude. So if I have a complex number such as a plus jb, then the magnitude is given by square root of a square plus b square. And therefore the form is similar over here. So this becomes square root of 1 square plus negative of omega RC whole square whole divided by 1 square plus omega RC whole square. And everything will cancel and we will get a magnitude of 1. Secondly, if we want to go for the phase value, then the phase will be given by tan inverse of negative of omega RC by 1 minus of tan inverse of omega RC divided by 1. So this is a simple rule that again comes from the complex variables where you have a ratio, let's say, of a plus jb by c plus jd. So the form is similar over here. And so if we do this little algebra, this turns out to be negative of tan inverse omega RC. That's the phase of that circuit. So the magnitude is 1 and the phase is negative of 2 tan inverse omega RC. And if we look at the options, option B is the correct one. Now, this is the second pattern of question. The third pattern would be that can you identify the type of filter? And with identification of the type of filter, if we recall that all pass filters are those filters which are phase shaping filters. They shape the phase of a circuit to which it is connected, but the magnitude always remains the same and it is equal to 1. So these are unity magnitude circuits, and therefore this filter is an example. This circuit is an example of an all pass filter. Now if we refer back to the expression, V naught S by VIS was equal to 1 minus SRC by 1 plus SRC. And so this is an example of a first order all pass filter. Also comes from the fact that there is only one capacitor which is present in this circuit. So it cannot be a second order filter. The final pattern of question would be that can you identify which is the correct pole zero diagram of this circuit? So this circuit had a transfer function of 1 minus SRC by 1 plus SRC, and it is very easy to show that if you set the numerator to 0, then the 0 will occur at S equal to 1 by RC. And if you set the denominator to 0, it leads to the occurrence of the pole, which is at negative of 1 by RC. And note that because this is an all-pass filter and because the pole 0 alignment is like so, the pole and 0 is at an equidistant from this origin. So if this is, let's say, x units, then the other one will also be x units. In this case, x is equal to 1 by RC. So this is one pattern of question where there could be a lot of varieties, and as we will see in the upcoming videos, there could be questions related to identification of filter types where the filter type might turn out to be a low pass filter or maybe a high pass filter, and we will also see what are the shortcut techniques to identify the filter type.